Hello, Build Stuff. Welcome back. So please, it is my great pleasure. Put your virtual hands together and welcome to the Build Stuff stage. Our next speaker, somebody who I've known and followed for many, many years, an expert on all kinds of things to do with software development, testing, architecture, culture. He's come to talk to us today about spearheading the future of program. Please welcome to the Build Stuff stage, Venkat Subramaniam. How you doing, Venkat?
Greetings. Thank you so much. You're very kind. I really appreciate it. I hope everyone is staying safe. It's a pleasure to be here.
All right. Over to you.
Awesome. Thank you. Excellent. Well, welcome everyone. Thanks for being here. I'm going to talk about what I would like to see in the future of programming languages. Well, I'm going to say there are probably two kinds of programming languages out there. The ones that are mainstream, which a lot of us are using, and those that are somewhat esoteric, but really powerful and interesting as well. Well, I program in about 15 different languages. What I'm saying in so many words is I'm not good in any one of them, but I'm really excited about programming languages. And I really came to programming for the science and math in programming. But after a few decades of programming, I'm still programming every day because of the art in programming. So I see programming languages from the point of view of expressiveness. How can we express our ideas into different forms? How can we code our algorithms? How can we be very efficient, not only at runtime, but as programmers writing the code and maintaining it as well? And that's what I want to talk about today is what are some of the things that I really like to see in programming languages. Now, a lot of these things are already there in different programming languages, not so much in mainstream languages, but they are catching up pretty quickly. And what I'm going to talk about today is something you may be able to see in mainstream languages within the next year, 2, or maybe 5 years or 10 years, depending on the languages you are using and the pace at which they evolve. But let's get to that in just a little bit. When it comes to really programming, they say that the computer world, everything changes really, really fast. Let's think about that a little bit to see if that's really true. So how are we programming in the new century? If you look at a lot of code we are developing, we are still using things like for I equal to 0, a lot of moving parts and noise in the code. And it kind of makes you wonder if that's what really is modern programming, kind of makes you wonder about it, isn't it? So we need to really rethink about how to program for the new business, for the new hardware, for the new challenges and the new architectures that we are really trying to exploit in the current world. Now, some things are really fundamental and difficult to change in general. For example, languages are Turing complete. That's something we value a lot because general purpose languages should be used for, well, general purpose to program just about anything we want to program. So that becomes really important from the general purpose programming languages point of view. On the other hand, when you look at the languages and the architecture of systems, we still have to deal and contend with the von Neumann bottleneck. And that's not going to go away anytime soon. We have had computer architectures that try to really minimize and alleviate the pain of it, but that's going to stay with us for a long time. We have to work with those constraints, if you will. But having said that, what about language paradigms? Well, when was object-oriented programming introduced? Typically I would ask audience to answer that question and I will get different answers. Some will say, 1995, some will say 1980. Well, it turns out OOP was introduced back in 1967. Now think about that for a minute. That was and of course, OOP became mainstream in about 1990 timeframe. That was a 23 years from the introduction of the paradigm to when it became really popular. If OOP was a human, it had a terrible neglected childhood until it was 23 and people said, hey, handsome, do you want to hang out? And that's a very long process at 23 years later. Well, it turns out Dahl and Nygaard two Norwegians introduced the idea of object-oriented programming. The term object-oriented programming was coined by Alan Kay, an American computer scientist, but the concept was actually invented by Dolan Nygaard out of Norway. Well, of course, it was a really long journey for that to become adopted into a mainstream paradigm in the 1990s. And of course, now we're all excited about functional programming. Now, I may ask you, when was functional programming introduced? And keep in mind, one of the very first programming languages, Lisp, is functional programming language. Now, the concepts behind functional programming, the lambda calculus, was introduced even earlier. Well, everyone knows of Alan Turing. Well, this was Alan Turing's professor, Alonzo Church, who introduced lambda calculus, that's right, in 1930s. Now, a good 90 years later, we are getting really warmed up and getting excited to saying, oh my gosh, we got to program in functional style. Now, so when people, look at this and say, why do things take so long for adoption? We're not talking about a few years here. We're talking about decades for things to become mainstream and adopted. And the reason for that is we take change in bite sizes. We as programmers don't completely abandon what we do. It's not practical often. And then we transition over in incremental fashion. We learn in deltas. We take these changes in bite sizes. And of course, habits really are hard to change. It almost takes a new generation of programmers to make changes to it. This reminds me of an experience I had. We start out really young. We are learning things when we are in school and colleges. We are a new programmer and we are thirsty to learn and change. And as young programmers, we often sit there and say, why are you doing it that way? Shouldn't we change the way we do things? And we challenge the people who have been doing it for a while. And then as time goes on, we become senior developers. And then we sit there and say, that's how we do things around here. And then we look around and see these young kids growing up to become programmers, and they start challenging. The cycle keeps repeating over time. And that's so funny to watch, actually. But sometimes it actually takes a new generation of programmers to really rethink and change the way we do things as well. And of course, now we are poised for a few big changes in our paradigm. The change actually started back in 2003 to 2006 timeframe. And that first change was in the hardware world, if you will. The engineers went up to their bosses and said, we cannot run this anymore. It's getting too heated up, and we have to really go to multi-core processors. Today, you cannot buy a machine with a single processor, even if you wanted to. Multi-core is the norm. And we are buying machines at an affordable price with several cores on it. I recently worked for a client where we literally had hundreds of cores in that machine. And they said, we'll get you something even bigger if you need arises. So with multi-core processors, multi-threading is truly on steroids. It's no longer multitasking, if you will. And of course, we have devices and handheld computers and serverless computers and so on, and that are changing the way in terms of hardware and the challenges and the business poses on us as well. So we need to rethink about what we need when it comes to programming. And of course, we have modern demands. We have big data, the cloud, the microservices, the machine learning, the Internet of Devices and technologies. So a lot of these things are changing what we need to do as well. And of course, we do have some answers to these questions. The revolution behind NoSQL, the MapReduce algorithms, the reactive programming, and so on have come along to really present us with higher levels of abstraction to deal with the challenges of the modern devices, the modern business, and the modern architectures as well. But I want to step back a little bit and ask the question, how are we really programming today for web applications? Look at the web applications we have been creating. So the old web has been the paradigm where it's a stateless request and response paradigm. You make a request to a web server, it processes your request, throws a response back to you, often HTML and sometimes JSON or XML. And then what do we do? On the client side, we receive it, we process it, and when we are done, we make yet another request to the server. Now, when we make a request to the server wakes up and does a fresh processing because let's process, if you will. And when it makes a request processing and sends a response, we start over one more time to make this process. How does that feel to program? I say this is like programming with Dory. What I mean by that is, remember watching Finding Nemo, the famous movie? Well, there was a character called Dory who would forget everything every few minutes. Hey, I'm Dory, how are you doing? And then a few minutes later, hey, I'm Dory, how are you doing? Well, that's what we are doing here, is establishing a connection and the credentials. And of course, we use cookies and we worry about people not allowing proper cookies and then all the other things that come with it. Now, we kind of wonder, is that the right way to program moving forward? I'm going to say the new web has been around for a while, actually. It just is not mainstream. And the idea that we are beginning to embrace more and more is rather intriguing for me. And that idea is this concept of continuations. And I cannot tell you how excited I am about continuations. And I'm going to say we're going to see continuations in programming languages as a mainstream concept within the next 5 years. And again, don't mistake me. Continuations has been around for a while now in computer science. There are a few languages that already have continuation. It just is not mainstream. So in continuations, what do we really do? We are no longer in that stateless request model and response model. Continuations is a data structure that remembers the state of a conversation. Imagine this for a minute. Suppose I see you walk out of the building in the evening and I ask you, how are things going and where are you heading to? And you say, finally, I'm going to go watch that movie that I've been waiting to watch for so long. And I say, have a great time, and I send you off. And the next morning, I see you in the lobby of the hotel, let's say, and I say, hey, how are you doing? You say, I'm doing great. And I ask you, how was the movie? And obviously, I'm talking about the movie that you went to the previous day. If you look at me and say, what movie? That's not going to lead to a good conversation. So in other words, we met yesterday. We spoke about where you're going. I know you were going to a movie. So when I ask you, how was the movie? Obviously, I'm talking about the movie that you went to yesterday. We continue with that conversation, even though it's been hours since our last conversation. Well, that is an example of continuations. Let's get a feel for continuations here, if you will. I know this is a little scary, but I think we can learn from everything in the world. And I'm going to learn from a little bit of JavaScript in here. Suppose I want to write a function. Let's call the function as foo in the traditional way of how we name functions. But I'm going to say for in this case, and I'm going to say constant element, of foo. And I'm using this as an iterator in here, if you will, in this code. So in this case, I'm going to simply output the value of e. But before I do, I'm going to say, in this case, in the loop. Now, obviously, I want to be able to loop through this function over and over and over, but I'm going to go back to this function, if you will, and I'm going to say, in this case, simply put the word entering the function. That's what I'm going to say. So I said entering the function in this particular example, but when I execute this code, what do I really want to see in this particular execution of the code is the question. Well, what I want to really see in this particular function is I want this function to be able to iterate as a generator. So I'm going to say, in this case, a yield, if you will. And what am I going to yield? Let's just yield a value of 1, if you will. So when I execute the code, notice what it said. It says entering the function in the loop, and then it said 1. But here's the charm of this function. And I'm going to say hello, again, 1. and I'm going to yield a value of 2 right now from this call. Now, the point I'm making here is, notice I did not enter back into the top of the function, but I entered right into the middle of the function. So it says hello again 1, and then in the loop and printed 2. But I can go further with this if you really want to. I could say hello again 2, and I could return back a value of 3, if you will. And then you can see how we are entering back into the function. Well, this kind of simulates the idea of a continuation. So here is a function, if you will. You enter the function in the top, but you leave it right here, and you go do some work, but you come back right where you left, and you do some more work, and then you leave and do some work. So this brings a concept of coroutines, if you will. So the idea of continuations, if you will, and also the idea of coroutines really are pretty intriguing. And I'm going to say more and more we're going to really see this idea of continuations and coroutines really become mainstream in the next few years. And I can tell you how excited I am to really see this take root. And why is this really important to think about? The reason I'm excited about this is apply that idea in the context of microservices, in the concept of web applications, in the concept of distributed computing. Well, that takes us to a whole new level. You make a request to a service, a web server or a web service or a microservice, but when you get a response back, you get back a continuation as a response. And when you make a request back again, it can pull the state of the previous request and continue from there. So it becomes a really nice way to have this interactive transactional session carried through in a conversation, not a transaction in the database term, but a transaction in the business term where you're able to carry through these steps of execution. So I'm really looking forward to continuations and coroutines become mainstream in mainstream languages moving forward, so that we can save the execution state and then return back to that point at a later time. So languages, of course, moving forward should make it easier for us, the programmers, to get our work done. So languages should make simple things simpler and hard things manageable. You know how some languages take simple things and make it so darn difficult, we forget what we were doing when we are writing the code. Well, good languages and languages that evolve should make simple things simpler, but really make hard things manageable along the way as well. So what are some of the things I really like to see come into mainstream? Languages must promote higher level of abstraction. Well, they already do to a great extent, but I want that to be pushed even further. And languages should promote composability and should really embrace more of declarative style of programming than imperative style of programming that's been predominant over the past several decades of programming. Well, let's talk about expressiveness of code. What if the code becomes intuitive for us to create along the way? Let's think about that really quickly with a little example here. Suppose I have some fruits with me, and let's go ahead and say this is going to be a list of fruits. Let's say we have apple with us, and we have some banana with us as well. This code is in Kotlin, and Kotlin is one of the languages which is very expressive and fluent. And I would like to see a lot of languages become that expressive and that fluent as well as we go along. And I'll give you two examples of expressiveness and fluency in here. So one is, I want to go ahead and print out here the fruits that we have in here. And of course, the fruits here are apple and banana that we have with us. But what if I want to add another fruit to this particular collection of fruits? And I just said, what if I want to add another fruit like an orange? Now, why shouldn't I just be able to add another fruit? Because after all, I just said add, and why shouldn't I be able to do it? And that's exactly what I want languages to do, is be intuitive and expressive when we write the code. In a similar way, switching back here to JavaScript, one of the things I really enjoy is this concept of destructuring. And I cannot tell you how much I am really thrilled about destructuring. So what in the world is destructuring? As an example, let's say we have a person with us, and the person has a first name, let's say, is Sam, and we have an age which is 2, let's say. Now, given this person, maybe it's coming from a function, if you will. So maybe we can write a function called getPerson, and the getPerson function, let's say, is simply going to return that person back to the caller. So we'll say return person. Now, what I want to do on my side is to use this person object. So how would we typically write the code? Person is equal to get person. We could get the person object on our hands, and then when we do, we can print out the person. But what if I really want to get the first name of the person? Maybe the name is called the first name, and you could write the code like first name, like so, and get it. And similarly, you could say output the person's dot age, and you can get the person's name and age. But this is a verbose code that doesn't really make me excited, because it takes a lot of effort and ceremony to get the coding done. Now, why not try something a little different? What if I simply can say first name, and what if I can simply say age over here? But obviously, those two don't exist right now. But what I can then do is perform this idea of destructuring. So what is destructuring? Well, structuring or construction is taking pieces of data and creating an object. Deconstruction or destructuring is the opposite of that. You take an object and tear it into pieces into the data you are interested in receiving. So what I can do in here is simply say, here comes the first name of this particular object, and I'm going to store that into the first name. Here comes the age, and I store that into the age. Well, this is destructuring, where we went from an object into variables, and I can change the name of the variable if I really want to, and I'm calling this as first here, and I'm going to call this as the age. As you can see, we can easily define local variables by destructuring this object. Again, many languages are beginning to provide destructuring as a first-class feature in the languages, and I want to see that more and more as time goes on. So I care a lot about the code becoming really expressive, if you will. And so expressiveness in every little thing we do. For example, as we iterate through objects, as we destructure the data, as we manipulate objects, as we work with collections, what if in every single angle it becomes really fluent, then becomes a lot easier to program, rather than spending the code at the lower level of abstraction, raise the level of abstraction and make it easier for programmers. When we are developing more and more complex applications for the demands of the business and the modern devices and architectures, we really need higher level of abstraction for us to be able to express our code. And so I really am looking for code that is more expressive. Now, the next thing I really care about is composability. And this is almost mainstream now, in my opinion. And that is one of the things that really excites me about, again, expressiveness of programming languages. Here is an example of a code in Java. And for example, in this particular case, if I have, let's say for a minute, a collection of numbers to work with. So I'm going to say, you know what, actually, let's take some names to work with. So if I say string, I'm going to say names is equal to list of, let's go ahead and say some names that I want to work with. Now, I want to be able to say, print print comma, let's say separated, names, in this case, of course, separated. And I'm going to say names of length, let's say 4, in uppercase. So if that is what I really want to do, I want the code to be really compose. And what does composability really mean? There are a lot of examples for composability we can think of. One of the famous examples is the Unix pipeline. So you could say cat, file name.txt, and then you could say grep, some word, and then you can say pipe that to wc minus l, and I want to know how many lines contain that particular word in that file. That's one example, if you will, of pipelining or composability. Composability is really where, if you really think about it, right? If I ask you, what is this? And you may say, oh, that's a pen. Yeah, you're right. But then you realize the pen actually contains multiple parts. It's got a lid, it's got a stem, it's got a casing, and we then go along and build this object, and we compose objects to have other objects. And then you can go to the next level and say that contains a casing, contains an ink, contains a nib, and then you could go a little further and say, oh my gosh, it contains literally billions of atoms and electrons and protons. Well, that's object decomposition, and we can decide what level we want to be in. In a similar way, if you really think about it, the idea of functional composition is extremely powerful. Suppose I tell you this is one function, and I tell you this is another function, and I have a third function with me. So yes, I have three different functions here. That's great. But I can take the first function and I can compose that into a second function. And then I can take that and compose that into a third function. And all of a sudden, I have a functional pipeline with me. And that's exactly what you're seeing in the Unix pipeline is the data goes through the first function, then it flows into the second function, then it flows into the third function. And we are beginning to see this composability take root in so many places now. You see this quite significant in Java in the Streams API. You see this in the reactive programming world where we are seeing this composability, and beautifully the data flows through a pipeline. Like, for example, I might take water and I may send it to a filter, which is going to purify, maybe we'll call it as a purifier, and then the water goes through a cooler so that we can get some nice cool water to drink. Similarly, I may take air and I'll send it through a purifier, hopefully not the same purifier in this case, but then I may send it to a heater, and then maybe I'll get a warm air into the room for a cold winter day. So this idea of this pipeline or functional composition is really prevalent, and we are able to think through our programming not in imperative terms, but in this flow of data through a pipeline of functions. And that's exactly what it is. It's a functional pipeline, if you will, and where the functions form a pipeline of data, of functions rather. So in this case, we can say, for example, output, and we can say names.stream, and then we can say filter, given a name of length is equal to 4. Then we can perform a map operation, if you will. And the map operation in this case says, take the string and convert it to an uppercase, if you will. And then finally, we'll do a collect on that particular function, and we'll do joining using a comma and get the response eventually. That collect joining comes from the collectors in the case of Java, but we can perform that kind of operation, if you will, and of course collect with 2 L's, even though I'm really excited about the collect function. So in this case, you can see it says Dory, Gil, and Nemo are the 4 names that we got from this collection. So if we can think of a problem as this series of pipeline of functions, it becomes a lot more expressive. The code begins to read like the problem statement. Given names, get me the names of length 4, and then get me them in uppercase, and then join them with a comma. Notice a single pass through, we are able to read the code. So composability is really important in a lot of things we do, and we want to see this more and more in almost every angle of programming. But of course, what good is all of this if the program is not efficient? So efficiency efficiency is extremely important. And how do we really make it really efficient? And this is where, when you look at this structure, you might be concerned, you might be worried to say, oh my gosh, this is going to be really poor in performance. Well, actually, it turns out this is not any worse than an imperative style of coding, if you will. So for example, if I were to take this code and say Boolean is of right size, let's call it as that, and I'm going to say name, and all I'm going to do is return the name, let's say in this case, dot, excuse me, pardon me, name dot length, let's say, is equal to 4, let's say in this particular case. And I'm going to go back to this code and I'm going to simply say sample is of right size and execute this code. Now, clearly it gave us the same result as it did before. Now, on the other hand, rather than printing this result out, let's go ahead and just simply run through this collection of data. And then when I'm done with it, I'm going to simply say over here, output, let's say done. Now, looking at this code, you can see that it's going to display the call to those names up here and get back the results. And when you run the code, you can see it says done. But if I go back here and say output, and we'll say called for, and I'm going to say name. When I execute this code, you can see it says called for all of those and says done. But what about performance? This is something developers often are really excited about. And the answer to that is lazy evaluation. And lazy evaluation is so important from the point of view of performance. And I want languages to embrace this more and more. As an example in here, again, this is in the context of stream, but what if this happens in almost every angle of programming where efficiency can be built into programming languages? So as an example here, if I run the code, you can see it prints all the data. But if I were to comment out just the last part, the terminal operation, notice it did not execute the filter on the map. Instead, it directly said done. That's laziness in evaluation. And that can lead to more efficiency when it comes to code. So a lot of optimization that can happen. The last thing I want to quickly mention here is that I want the concepts to be almost seamless asynchrony. Well, I'm going to bet myself on this. You know, we've been favoring parallel for a long time, but I think moving forward, asynchrony is going to play a bigger role than parallel programming. You know, sometimes we hate to admit it, but I want to emphasize JavaScript got this right. JavaScript emphasized not parallel and multi-threading. They emphasized asynchronous programming way from the beginning. That's brilliant, because 20 years later, 25 years later, we are saying, oh my gosh, we need more asynchrony thanks to the world of microservices and the type of applications we are developing today. So asynchrony is important, but I want almost seamless asynchrony. So what do I mean by almost seamless? So to give you an example of this, let's switch back here to Kotlin. Suppose I create a task one here, and I'm going to simply say in here, entering, let's say entering task 1. And then, of course, I'm going to simply say exiting task 1, let's say in this case as well. Similarly, I'm going to create a task 2, which I'm going to say is entering and exiting also. So in this case, I'm going to simply go ahead and run these two tasks, if you will. So I'm going to call task 1 right now, and I'm going to call task 2 as well right now as well. And then I'm going to simply print out called them, let's say. Well, if I execute this code, it's going to enter 1 and exit 1, enter 2 and exit 2. So there's not going to be any surprises for us in there. That's exactly what the output really shows, as you can see. But what I really want to do is to turn this into a coroutine and continuation by calling, let's say, run blocking. And then within this, I want to call a launch on this one. And I'm going to launch these two tasks, if you will, so that they can run asynchronously, not necessarily parallel. It could be concurrent or in parallel. So for this, I'm going to import Kotlin x dot coroutines, if you will. Well, this is going to launch that into a coroutine, but it's still going to run in the main thread. So that's not going to be really a big deal at this point. But having said this, though, this is just to entertain this thought a little further. Let's say thread.current thread, if you will. And then I'm going to, of course, in this case, display the thread information in all these execution. Should be no surprise. They're all going to run in the main thread, if you will, because it's really a continuation running across as a concurrent execution. But notice I enter task one and exited task one. But what I really like to do is I want to yield while I'm in the middle of this call. And similarly, I want to yield while I'm in the middle of this call. So the question is, how can I actually yield between those? Well, that really gives us the ability for us to do some task, but give opportunity for another task to execute while we are blocking maybe on an I/O or a database call or file access or talk to a remote web service or a microservice. Well, this is asynchrony being brought in. This code will not work at the moment. And the question is, why wouldn't it work at the moment? What is the reason for it really failing? And if you notice, this is what I meant by almost seamless asynchrony. The problem is, when you're changing the programming model, when you're changing the semantics of your code, you want programmers to be aware of it. If a programmer is not aware of change in semantics, it results in unexpected behavior. Unexpected behavior is not wrong, it is unexpected. And the languages should not lead to code that deviates from programmers' expectation. So this is why that almost seamless. I don't want things to work by itself. I want things to almost work by itself. So this is why Kotlin says we want to use a suspend keyword to alert the programmer, hey, this code is a little bit different from your regular semantics, be warned. So by putting the word suspend, the code actually works right now, but notice we entered task one, didn't finish it, entered task two already, then came back to finish task one and finish task two. So that kind of seamlessness is extremely important, and I want language designers to embrace that moving forward, because you don't want to surprise programmers by changing the semantics on them. The syntax should give a hint on the change in semantics. That is really important for languages to really help programmers who are embracing those languages to do bigger and better things. So how can we prepare for the future? How do we get ready as programmers to prepare for that future? And to this, I'll give us a story that I came across recently that blew my mind. This was a study done in Chicago, and they took small children, and they were doing this study using the children, and they had two groups of children. The first group of children, their parents spoke a language, their friends spoke the same language, everybody they came in touch with spoke only that one language. The second group of children, their parents spoke one language, but their nanny spoke a different language. Their friends in school spoke a different language. Their teachers spoke a different language. And their playmates in the library spoke a different language. So these kids were speaking one language with their parents at home, but they were exposed to hearing other languages continuously from other people they interacted with. So one had a diversity of languages, natural languages. I'm not talking about these children programming in programming languages, natural languages. The other group did not have the diversity of languages. Well, what the researchers did is they would take these two groups of children. They would put objects in the room. Let's say, for example, bananas. And they would put banana between the person doing the research, the researcher and the kid. They'll put a few bananas, let's say 3 bananas, and they'll put a banana behind the researcher. And they would ask the child, how many bananas do you see? And consistently, they were blown away by this observation. The kids who spoke only one language and were exposed to only one language will say, I see 4 banana. 3 in between them and 1 behind the person asking the question. On the other hand, the children who were exposed to multiple languages almost always answered 3 instead of 4. And they were intrigued by it because these small children, they don't know a lot of stuff. and they were not given an instruction, but those children automatically looked around the room, found 4 bananas, and immediately realized the person asking the question is not seeing the banana behind them. The 3 bananas in front of them are the ones that they both are seeing. So they were able to filter out. So the researchers are saying when the children are exposed to multiple languages, they don't think in their own terms. They actually think in terms of the other people's viewpoint as well. This leads to better empathy. This leads to better decision making as well. Well, I'm no expert in anything, but certainly I'm no expert in natural languages. But I'm a big fan of programming languages. Like I said in the beginning, I program in about 15 different languages. I can vouch for it empirically from my own experience. When I used to program in one language versus when I started programming in multiple languages, I have a diversity of my viewpoint, and the way I think and the way I design is very different. Not only that, by embracing these different languages, it also helps me to adapt to languages in the future much more effectively as well. So I'm going to conclude by saying that the amount of time we need to learn a new concept is inversely proportional to the number of diverse ideas we are exposed to. This was intriguing to me because I was spending time with a group of developers in a company I was doing training with, and there were 2 developers who were a little bit older than me at the time. I think they're still older than me today. But those 2 developers, of the same age, but broadly different experience. One exposed to different languages, the other who was not. And in this case, when I present an idea, the way they absorbed it was very different. The one who was not exposed to ideas found it painful. The one who was exposed to different ideas was eager to know the differences and go deeper into the concepts. And I realized, and I tweeted that day, and I said, the amount of time we need to learn a new concept is inversely proportional to the number of diverse ideas we are exposed to. So the more we diversify our knowledge portfolio, the better we are in adopting and adapting to the change in the future. So learn different languages, not to use them all. I don't use all the languages I know, but I use the ideas from them quite a bit every day. So learn different languages, not to use them all, but to be able to adapt to the change quickly and easily as the languages we predominantly use every day begins to evolve. So learning different things and diversifying is a great way to keep up with that as well. So don't wait for the future, and that's the exciting part. It is already here. And that is the beauty of what we do is, if people ask me, what is my job? I tell them my job is being the kid in the candy store, where the candy to me is programming. And so that's what is exciting. It doesn't matter how old you get, you still feel like a kid because the technology is awesome for us to be able to play with. But to really honestly, to wake up every day and say, oh my gosh, I did not know that. It's so exciting. I learned something more today is really rewarding. And we should really be very, thankful and privileged to be in this field. Let's make the best out of it. I hope that was useful. Thank you so much for joining. And you all have a wonderful rest of the conference. Cheers.
Thank you, Venkat. That was really, really cool. So we have a couple of minutes for questions here. We got one question in the stream from Oliver, which is actually, it looks like somebody's already answered it in the stream. Oliver says, is there a good way to debug stream processing in Java now out there? Almantas has answered that IntelliJ has this. You got anything to add to that one, Venkat?
Yeah, I don't know the answer for that because I don't write code with bugs. Just kidding. So there are 2 answers I will give. The first answer I will give is the answer that you already got, which is a good one. Use IntelliJ. But the answer I would like to reach for is, one of the problems with the code, if I ask you, is it hard to debug Java? You're going to say no. But if I ask you, is it hard to debug multi-threaded code? You're like, heck, really? You want to debug multi-threaded code? What's wrong with multi-threaded code? It's not that it's hard. It's non-deterministic. So in other words, the first thing, there are 2 things I would say. The first is learn the semantics, know about lazy evaluation. And when you know about lazy evaluation, you know when things will be evaluated. That helps. Second, do not permit any developer in your team write a multi-line Lambda. That's where the disaster really is. I blogged about this once and I tweeted. If you Google for it, you'll find it. My tweet said, Lambdas are glue code. 2 lines may be too many. So Lambdas are glue code. 2 lines may be too many. So if we write Lambdas really small, then the Lambdas will have to call other functions. Then you can put the breakpoint in those functions and debug the way you normally debug. So it's not going to be really that hard if we have a bit of discipline to not let Lambdas grow bigger.
Excellent stuff. Thank you. And yeah, very positive feedback. Well, you got a lot of little thumbs up emoji, but that's the online equivalent of a standing ovation and round of applause, you know? Great stuff, Venkat. Thank you very, very much for being part of Build Stuff here online.